Hello there, welcome to the wonderful world of radio frequency and electronics engineering. On the bench today for repair is a Rohde Schwarz CMS33 radio test set. This particular test set has got an issue with the variable control when it's on a particular parameter that the variable control can adjust. It randomly just shoots off by itself, changing its own value without you touching that. And also the screen's flickering until it warms up and you can hear like a little electrical spark inside as it flickers, so as if there's a loose connection or something like that occurring. Anyway, we're joined today by the technical manager, who's just to the right of the camera, and he'll be no doubt giving us some technical advice and obviously giving some kind of an input into the fault condition later on. So yeah, we'll have a look at it, we'll switch it on, see if we can get it to replicate its fault, and then go from there. Okay, here goes. Flick the switch. See what happens. Okay, so let's see now. If we go to say RX test, if we go to RF level, and then obviously we can see there when we zoom in on the screen, we've got a level there that we can adjust just here. Now when I turn the control, obviously if I turn it clockwise, the level, obviously as it's doing, it's working at the moment, it's behaving itself, and if I turn it, there we are, look, it's started to adjust itself, so I'm not touching the control now. It's just so when it gets a certain way around on that control, you sort of get to the 3 o'clock, the 6 o'clock position, and it starts not to adjust itself properly. I'm going to go back the other way now. It's calling me a liar, starting to behave itself. Anyway, if I just left it like that, or I typed in a value like neg 115 dBm or something, dBm, and then say I left it like that for a moment, this will just start at random varying itself, and that's what it was doing. Noticed as well the display is behaving itself. The backlight would be flickering normally when it starts this problem, so it could be the fact that I've just moved it off the bench up there to bring it down onto the service bench, that disturbing it has actually sorted it out, which is, knowing my luck, that's probably what happens. But obviously if I tap it or whatever, I'm not getting any changes at the moment, so I'm going to have to wait till it starts playing up and then come back in the video to show that particular thing. I mean, it's obviously on the bench here, sandwiched between 2 radio test sets, so the weight of the other test set on top of this one may have you know, caused a bit of strain on the chassis, and it bend something inside a little bit or whatever, or disturb something, or maybe just me getting it off the bench might have disturbed it, and naturally it started to work. But it was saying when you went to set frequency as well, if you typed in say 145 megahertz, and then you obviously tried adjusting the frequency with this control, then it would at random start going off. When it does it, it obviously starts beeping at you, particularly when you're on the level, because it's trying to go to a level that's well below where it can actually get to, because it goes down about neg 131 dBm, and that's what it does. It just flashes up that the value being too small message all the time. It does that permanently. And of course when you take the control back with your fingers and try and turn it to, you know, get it back to where it should be, the value doesn't change, and you're having to try and stop it by grabbing the control, the rotary control, and pulling on it outwards as you turn it, or pushing on it quite hard and turning it and trying to wiggle it while you turn, and then it sorts itself out. It starts working again then. But occasionally you see the value. Oh, here we are, look, it started. There we are, look, it started. So that's not right good, is it? So if I just switch that off a second. So no matter what you do with this variable control, so I've turned it to the right, so we get it to neg 130.8 dBs, and I'm turning it right, and the levels drop now, you see, it's coming up too small. So as you can see there, so if I just try turning the variable control clockwise, you can see it's trying to adjust the level, but it's funny, at a stage it does try and adjust it, but then it jumps back. Now then it starts behaving itself a little bit, but then it's going erratic again now. It's zooming the other way, it's going up to maximum RF level now, and then it'll get to the top of a maximum RF level, because obviously I'm not touching it, and it'll start saying it's too much now. So if I turn it the other way, minimum RF level, and it's just, so it's either extremes of one way or the other. But if I grab hold of the control and just wiggle it a bit, see, this is Rohde Schwarz quality control for you. The foot's just dropped off it. But anyway, if I grab hold of this control, and now you can see the display is just flickering, just started to flicker. You might be able to pick that up on camera, the backlight of a display. It's funny how the two faults occur at the same time. But anyway, if I grab hold of this control and give it a wiggle, I can at times get it to play ball, or it'll suddenly start working. It's really weird though, I must admit. So it doesn't matter if I spin the control, because these Rohde Schwarz controls, you can spin them as a wheel, you know, because they're light weighted. But anyway, it might be it just needs a clean, or there's a dry joint somewhere, or a bad earth that's also affecting the screen. I can't get to, now it's working, you see, because I spun it really quick. It's as if it cleaned something up, and then you'll get to a certain point on that control and it'll start doing like it's doing now. So it's like the control will work. I've had it where the control works from say 6 o'clock to 12 o'clock, and then once you get it past 12 o'clock going towards 3 o'clock to 6 o'clock again, then it starts going funny, and then you grab hold of it like there, it's adjusting, and then suddenly it goes off on one. So it's as if the control's got some bad notches on it, and I've yet to find out. I think that's an optical control that's got a decade output on it, pulses high or low depending on which way you turn it, but I'll have to look at the service manual on that because I'm not 100% certain. I know the Marconi radio test sets, it's an optical encoder. I don't think it's a binary coded decimal switch control with any data outputs on it, but I could be wrong. We'll just have to look in the manual. But if you spin it really quick like that, sometimes it sort of sorts itself out, it cleans itself up if you like, and then starts behaving itself. Or if you push on it like that, I've tapped it in, it's stopped it because I've just tapped it in, and then when I turn it, you can see it sets it off again. It just starts to work. That's a notch, because there's little notches and increments in it. Then suddenly it just takes off again. So it's quite a strange little problem, you know. And as I say, the display flickers a little bit when it does this particular problem as well. So I think that's got something to do with it. So it'll be interesting. We'll have to strip it down obviously to get in. We'll have a look at the manual and see what we can do, but it's yeah, not particularly good. That, see, it's stable now. If I just turn it counterclockwise, it's working. That's a notch. That's it, you see. So you've only got to go a few notches with it. It starts going off. It stopped itself. Again, counterclockwise, few notches, and now all of a sudden it's jumping all over. It's going in big increments. So just we're about the 6 o'clock position there, and then it's just trying to continually adjust itself with the look of it. So it's weird. Anyway, it's only the variable control that's affected. It's nothing else that's affected. So yeah, very, very odd, very strange little problem. So we'll have to have a look at it and see whether we can get it repaired. Interestingly, on the inside lid we've got a bit of a diagram, block diagram, but as we can see down at the bottom here, we've got some information about the configuration. Obviously we've got the display here with 2 ribbon cables which connect to the display to the digital section, this module here that stands inside. We've got the ports on the front, obviously. I think that's the memory card, which is obviously that slot on the front, and there's the internal reader. But I'm just trying to find, obviously we've got potentiometer here for the contrast and brightness control, which appears to be there. Variable, that's the variable control, which according to this looks like as if it's got a connection all the way back to the speaker, which is just off the top of the screen, just here. There's a speaker up there. Looks like it's on some kind of data bus, because we've got this ribbon cable here, X2, that goes onto the motherboard, and the motherboard signified by this square here. Looks like it's got a motherboard connection, and there's a data bus then that's shared amongst all these modules on the motherboard. So it looks like as if the variable control shares that connection along with the contrast control and the speaker and other things on that flex, and also it may be that there's a dry connection on there, a dry joint or intermittent connection or something like that possibly. So that's interesting, but at least it doesn't go direct into digital section. It goes to the motherboard first before then going to the digital module. So that's a little bit of information that we didn't know before. Okay, so obviously I could do with getting to this control here on the back to do some measurements, but and obviously take a look at this display in more detail. Ideally, I don't want to take the front cover off if I don't have to, because that's going to involve quite a bit of work. So anyway, I've looked at the service manual, which we'll look at together very shortly, and we've actually got 2 modules at the front, and the first module here is the measurement module, which does all the digital analog measurements. But the very first one, this one here, where this ribbon cable crosses and these 2 connected, is the microcontroller computer. So we basically got 2 flexes here which lead off to the display and the keyboard, and then we've got this ribbon cable which goes to the back, which connects to the rear board here, where I think it gets again some more digital in out on that that flex. So I've disconnected a bracket that was here We've removed these connectors. Quite a simple process of just backing these catches off there and letting the flex come out, so that we can remove these two modules, because if I can get to the rear of the display unit without having to remove the front, then that will be a big advantage. So I'll just flip it over on the other side and then we can take a look on it's underneath. Okay, so what we've done, we've removed the two modules that were here, which is what we've got now unplugged from the motherboard. They're quite easy to remove of these modules. We've got the front processor module, which is this one here, which is entitled the digital section. So that particular module sits right at the very front, and this ribbon cable sort of sandwiches between the front panel there and the module as it goes in like that. So to be careful with that ribbon cable, just remove it before you pull the module out, because it gets trapped between the front panel and this module. And the other module, which sits behind that, more towards the back of the unit, so it's sort of a second module that's fitted in, is this one, which is entitled the measuring section. So this module is the measuring section. Now you'll notice that on all the modules there's these legends which go into detail of to which connectors go to which sockets. So when you unplug the cables, which we'll look at in a second, the cables are marked with an X number, reference number, on a band on the cable. So that marries up with the sockets on here. The majority of them all are SMBs on most of the modules. There is a SMC connector on one of the attenuator modules. So if we just turn round the unit so we can have a more detailed look. So firstly, how you get the modules out on these CMS series of radio tests, it doesn't matter what version of Rohde Schwarz radio test set you've got, they're all the same. There's these brackets here, and each bracket is held with two screws. So all you do is you just slacken the screws off, and right at the top of the bracket, you might just be able to see it if I just tilt the test set in the right sort of way. You can see those hooks on the top there, these little hooks, and they hook into the modules to prevent them from coming loose and dropping off the board. So what you do in order to get the modules out is, once you've undone these screws and slackened them off, this bracket slides back just like the one at the bottom does, and when these slide back, then they allow the module to come out. Now earlier on we were talking about this, where we've got SMB plugs which push fit onto the connectors, and they are marked with an X number on them, and you can see there that's marked as an X number on that particular module there, X203 I think it is, looking at it through the camera. So that would plug into obviously X203 on the module, so long as you get one module in first and then connect the cables to that, because the other modules are so snugged up against one another. If you put all the modules back in at the same time, you won't be able to see the legend on the side of the module, because as you can see, the legend's written on the sides, so the other module would cover that. So you have to put one module in at a time in order to reconnect these connectors. Now, depending on what modules are fitted, depends whether they've got SMB and SMC connectors. Now, SMC connector on this one is this one here, this silver connector. So this is very much like an SMB, where it partially plugs on, pushes on, and then the last part of it to get the socket to go home is you turn that nut. So an SMC is very similar to an SMB, except it has a screw thread at the very bottom of the push part of the action when you push the socket on. So SMBs are just push fit, obviously, because they've got a dedicated collar which just pushes on and then clicks on. So that's the difference between an SMB and an SMC. Now, I can actually show that in better detail. I have a box of SMB and SMC adapters, so I'll be able to show you the differences. But that's just something to watch out for on these test sets. There is obviously SMA connectors as well, which is this one here at the bottom of the picture. That's an SMA. You've got SMC, and then the rest of them tend to be SMB. And that's quite common on nearly all Rohde Schwarz products, is SMB connectors. But it's always worth knowing that, obviously, if you need to make test leads up and things like that. Now, because we've got the modules out now and everything unplugged, I can now show you internally within the front of the unit. Now, what's interesting about this is we've got the display board, which is made by Optrex at the front here, this green board. But when I took the modules out, I noticed something which may answer the reason why the display backlight was flickering a little on the radio test set from time to time. And this module here is the inverter module for the backlight, the high voltage buck converter for the backlight, which is this filament here, and then there's another filament as well, I believe, which is towards the bottom of the display down here, which is hidden. But that particular backlight is powered, this module, by this connector here. And this connector just literally, as I was taking the module out, just fell apart. Now, what's strange about it is that when you connect the connector back together, and this connector provides power to the inverter module. So basically we've got probably a low voltage 12, 24 volt whatever connection here that powers this module, and then the output of that module then is literally, it just drops apart, you see, that power connector. But anyway, the output of that module goes to this wiring loom, these wires here, to this connector, and then goes to the high voltage white wires, which connect obviously to this backlight assembly. So I'm sort of hoping, fingers crossed, that the reason why this module here that supplies power to the backlight, the possible reason for the backlight flickering, is because of this having a poor connection. So I probably need to back these pins out, and then because the pins are like that, and then the pin on the pin goes in like that, I think the receptacles are too far apart, which is allowing the pin to come out. So I probably need to back the pins out that socket plug, and then squash the receptacle a bit closer so that it's got more of a grip onto the pin. So that's probably the reason why. It's very flimsy, bit of a bad design really, but yeah, it just literally comes apart without having to do anything. So yeah, a little bit wrong. I'd like to take that module off if I can, so I can get into it and just check to see whether there's any components that are raised in their capacitors and things like that I can replace while we've got it apart. It may be that it's potted though, so we'll have to look at that. Now as for the variable control, that's just under here. That's the control variable optical encoder or whatever, which we'll look at in the service manual. And if we turn the control, you'll be able to see the washer. I can see the ball bearing in it as well, which gives it its notch. There's like an incremental notch feel to the control as you turn in it. It's got these little notches in it like that, as you can see as you turn in it, which is made up as the whole circumference of a turning circle. So this looks like it's quite a thick assembly, because on the other side there's a piece of plastic about that thick, which is on the top of the board, and I think this is a connector for it here, which goes to this ribbon cable. There's a ribbon cable which connects to this. There's a socket separate, If we just turn it back round again the other way, we can see down there, very deep down here, I can just zoom in a bit, I think, hopefully, might be able to see a bit clearer detail in there, but we've got this sort of ribbon cable that connects to a socket down there, which is soldered onto those pins. So, and I think those pins there connect to that socket. That socket ultimately connects to this ribbon cable, which then comes down and plugs into the motherboard here. So that's how it connects there. So it is looking possibly, depending on what I read in the service manual, that we may have to remove a front cover to get to that more, because I've got a feeling I'm going to have to take that encoder out of the unit altogether. I'm going to sort of have to take the front panel off, remove this encoder knob, and then the encoder assembly, and remove it if we need to strip it down to clean it, which is probably what's needed. So yes, that's going to be interesting. I'm going to see what's involved with doing that, but I think the next step is to look at the service manual to see what tests we can do in order to test that encoder while it's in circuit and it's connected without having to remove the front panel. So I'm going to have a look at that next and see what we can do, if at all anything. Back soon. Okay, so just to show the difference between SMB and SMC connectors, firstly you'll notice the one on the left just is a straight collar, whereas the one on the right has got the thread on it. As you can see there at the bottom, there's a thread. Now what's interesting about these connectors is, and I've often seen engineers over the years try and rive on SMBs on an SMC, which I'll show you, but this SMB here, which is what we find on these modules in this radio test set, this is an SMB plug. So that plugs directly on, it just pushes on and it clicks, and then it's on, and that's home. And as you see, there isn't a nut on this, so it's not meant to be twisted and connected that way. It's just meant to be push fit, so then we can remove that from that adapter. So that's an SMB. Now then, if we just try and find our SMC, which I've got here floating around on the bench somewhere. So that's our SMB connector there, okay, which marries with this. Now the SMC on the other hand is very similar to the SMB. So this is an SMC because it's got the screw thread at the bottom. Notice we can take the SMB and we can still try and plug it on, and this is where I've seen engineers going wrong over the years. So it partially pushes on, but because of that screw thread at the bottom there, it won't go home. And there's a good reason for that, because it's a wrong plug for that socket. So in order to do that properly, unlike some people I've seen over the years who try and push them on and then damage the plugs and sockets, you need the right tool for the job. So this is an SMC. You'll notice very similar in appearance to an SMB, but it has a nut on it, which you can see just here, this nut. So that connects to this SMC adapter, goes on, and then basically you just turn that nut then in order to make it go on for the last few turns. So that's on now, and that won't pull off. You tend to find the SMCs in aerospace applications or defence equipment, because obviously they're high vibration of it shaking around in things like when I've taken missiles apart and things that are ex-defence, military and avionics communications equipment, things like that tend to have SMCs because they have to lock on and be torqued up, whereas an SMB technically, because it's push fit, can shake off. So you tend to find in aerospace things like satellites, defence electronics equipment, all those kind of things tend to have SMCs on them, whereas non-vibration environmental pieces of equipment tend to have SMBs on, because the push fit is adequate for that particular application. So an SMC does look remarkably similar to an SMA in many ways, because of it having its nut, and it's very similar to an SMA. And I think I've got one here which I had a moment ago, and I put it back away. Let's have a look so I can show you. So this is an SMA connector, and so as you can see there is a size difference between them, but you can mistake an SMC for an SMA, but it's smaller than an SMA. Very similar insofar as its appearance of having a nut, because an SMA male has a nut, but as you can see it won't physically connect because it's smaller. So that's just a little thing to look out for when you're dealing with these pieces of equipment as well, test gears, that you've got a difference between an SMB and an SMC. Is the SMC has a screw thread, whereas the SMB doesn't. And don't mistake an SMC plug, which is smaller than an SMA, and don't try and connect that to anything else. Now, if you try plugging that onto the SMB, an SMC on an SMB, it does plug on, but it doesn't go on with the same resistance. It's loose. It's not the same. So there are differences between them, and it's important that you know that, because otherwise you could cause damage to your equipment if you don't abide by the right plugs and sockets. Okay, just got the service manual open now. I'm just taking a look. I managed to find, just in this block diagram sort of area, this modular diagram. Obviously the motherboard there, and we've got this ribbon connector which we were looking at just a few moments ago, that connects to a socket here. This W16 connects to this X31 socket, which is what I pointed out on that PCB, which then connects to X1 daughter board, and then we've got the volume and contrast potentiometers, which are these resistors that connect to this board as well, and the VAR, which is the variable control, isn't referenced with any connections. So at this stage it doesn't give us enough detail as to how that works, how many pins are on it, how we can test it, that kind of thing. Just shows the modular connection. So just need to dig a bit deeper now, I think, in order to find out some further info. Okay, we seem to have found some information. Anyway, looking at this in a bit more detail, it says here the spin wheel consists of a magnetic plate with 12 north and south poles, 2 parent magnets for the detent, and 2 Hall generators. When turning the spin wheel VAR, 2 square wave signals that are shifted in phase by 90 degrees with a pulse duty factor of 1:1 are applied to the 2 lines RMK1 and RMK2. It says attach 4.75k ohm pull-up resistors to X1.4 and X1.3. The signals, 24 pulses per rotation, are evaluated in a gate array in the digital section. But in the checking section here, it says attach 4.75k ohm pull-up resistor to X1.3 and X1.4. When the spin wheel is rotated, it must be possible to measure a square wave voltage with a pulse duty factor of 1:1, a frequency of 12 volts per minute by 3600 Hertz, and a phase shift of 90 degrees at outputs X.1.3 and X1.1.4. Deviations from the TTL level at outputs X1.3 and X1.4 indicate that the Hall generators B1 or B2 are faulty. If the phase shift deviates considerably from 90 degrees, the adjustment of the Hall generators is incorrect. So that's all it says about that. So it could be, because we managed to clear the fault by spinning the wheel really quick, whizzing it round, and then it came back when we started to use the control more slowly. It could be that there's some iron filings from these magnetic plates that have broken off and are actually stuck to the Hall sensors, in which case it might be giving the impression to the digital unit that we're permanently turning the control either clockwise or counterclockwise, which is the fault that we saw earlier when we're manipulating that control. When we spun it really quick, it seemed to clear out itself a little bit so that it behaved, and then as we just adjusted it a few notches or detents one way or the other, then it started within a quarter of a full turn then playing up again. So it could be that there's iron filings or some foreign debris in there that's magnetic, that's sticking to things that it shouldn't be, and it's giving a false signal, and thus giving the impression that we're spinning the control when we're not. So it still may mean, after all this faffing about doing these tests, that we're still going to strip the control down in order to clean it inside. So, but we can do these tests anyway and consider this, and then take it from there, I think, and see what we're going to do. Okay, so this is a schematic diagram now for the Hall effect sensors that are used in the spin wheel variable control module. So we've got the magnetic disc, and as it said earlier in the in our explanation, that this disc comprises of 12 north poles and 12 south poles, and obviously as a south pole comes via the bottom Hall effect sensor, it would then create a pulse, and likewise at that point there would also be a north pole that would pass this sensor more likely, and that would then generate a pulse out of phase to what would be on the south pole sensor. And so I think, although it says there are 12 north poles and south poles, I think there's a total of 24 detents in the disc. So each notch would mean that each sensor would measure both a north and a south pole, and thus when we turn the control clockwise, the pulse train being measured by the digital circuitry would represent a clockwise motion, and when we turn it anti-clockwise, then naturally that pulse train will essentially reverse in the opposite direction. So this is where it talks about that 90 degrees out of phase. So if, for example, there is foreign debris off this rotary magnet that's got off, broken off, some filings or something that's stuck to one of these sensors, then it would essentially trick the digital circuitry into thinking that the control's been turned permanently one way or the other. And that's why when we physically rotate the control on certain levels, for example RF level, frequency, etc., if you remember, it just incremented continuously even after we'd stopped turning this control. And what happened is that it continued to increment the value until it got to its maximum level and stopped and said value too large on the screen. And likewise, when we turned it counterclockwise, the value decremented to its minimum level, where again it said value too small. So I definitely think there's some merit in this, where there's either some magnetic materials that have got stuck to these, contaminating these sensors, and it needs a clean probably, or some foreign debris got in, like iron filings or something like that, and it's picked up round these. Or it could be the sensors themselves, how they're positioned in the control, may have become detached from where they should be and are floating around in places where they shouldn't be, and thus picking up false signals from this magnetic disc, and thus creating this false symptom. Now we have, as you'll have known earlier, when we spin this control really quick and we whiz it round this spin wheel, it sort of clears a fault away, and then it's only when we start turning it slowly again and we get it sort of quarter to nearly half a turn round that it actually starts playing up. So I believe that there must be some merit in the the formula I'm coming to where these are contaminated or repositioned inside, they're moved about, or something's gone wrong. So even with a pull-up resistor on these lines, as it suggests in the thing, because obviously it's TTL, which is 5 volts level anyway, we should be able to see a pulse train on them, but I think it would still indicate that these sensors have got some contamination or something. So at the end of the day, we still might have to strip it down in order to clean them out anyway, and have a look inside and find out what's going on with these little Hall sensors. Back soon. Okay, so I might be able to get this board out where this control is, because that's X1 there. That's the connector that it talks about in the diagram, and it said X1 pin 4 is 1 Sol effect sensor, and pin 3. So if pin 1's on the top there, it's one of these pins here. But the trouble is, when we've got the modules in, I can't see that because it's hard up against this front part here anyway, so it's immaterial at the moment. But I think the screw, there's 2 screws actually. There is this screw, and then the one diagonally from it there, and then this board comes off after the control knob's been, well, the rotary control knob on the front's been disconnected. So I might be able to remove this board without having to strip the front of the test set down. So I'll just look into that next, see if we can get it off, and then take it from there. Right, so just count how many detents there are in this rotary control, starting with this reference point in line with this key. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So there must be 12 north and 12 south. Otherwise it would obviously be 6 north and 6 south if we did just 12 detents all the way around, but because there's clearly 24 detents going all the way around, must mean there are 12 of north and 12 south poles on that magnet. Okay, so we're getting down to the finer detail now of being able to get the front off. So what I've done so far is I've removed all the chassis screws that hold the front panel on. So there's screws here, a screw down here, and then basically on the sides here we've got the strap that we have to remove because there's a screw which then will allow the front to come away, and then there are a few screws on here that you remove, and these screws as well as 2 screws in there, 2 there, which then allow this, you know, to front to come away, and same on the other side. Anyway, once you've done that, then the front's good to come off. The problem being is this rigid coaxial cable here, this metal silver coaxial cable that goes to the N-type on the front, and it goes up there to the attenuator that's mounted about halfway up here, which is you're probably able to just see it there, look, and that's the connector there. So the coaxial cable goes up and connects to the attenuator, 3 dB power attenuator. Now, because the design of it is such that it appears it's fastened from behind is this connector, so if you look up here and perhaps zoom in, you'll be able to see, if I just twist this round a bit better, there's a nut on the N-type. It's just there, this nut, and the type N-type is bolted on at the back here, so we've got a nut at the back on the larger circumference. So if I undid the smaller nut that you can see on the back of that, if I undid the smaller nut where the coax goes in, that would allow the coax cable to be withdrawn from the socket whilst leaving the outer shell of the socket still fastened to the front of the test set when the front's removed. I can't get onto this because when you look at the depth, trying to get something into here to turn, there's just no turning space. Technically a pair of long nose pliers might be able to do it, but it depends how tight that nut's on, and it's going to chafe it up and make it look quite bad. So I think the easiest thing to do, because the front won't come off unless you remove this, is to probably disconnect the cable up there, pull the cable out, bend it out so that the front then can be withdrawn from the front. Now in the service manual it goes into detail of how you can do this, but if I just back this off, there is in the manual instructions to take out all the little screws that go there. There's a screw down here that you take off as well. I'll just turn it over so it's easy to see in this illustration, but it's rather bizarre. So now these little screws that are painted the same colour as the front of a test, there's one there, one there, one there, there's another one there that's not painted the same colour, that's in the variable control area, and there's another one somewhere else. Oh, there's one there as well, and that's about it. And then there are 4 screws, one in each corner of the test set, in the 4 outer corners. Then you can remove this front panel, and there's a flexi goes in the top, and this then can be withdrawn from the front of a test set. Now what's interesting, if I just try and remove this very carefully, this connector, I don't want to cause any damage to it because it's easily done. There's this flexi, this connects to the keyboard, you see, so that removes. This ultimately is a keyboard membrane assembly. Okay, so then that relieves us with the very front of a test set, and as we can see, normally on most test sets you'd have a nut there, and then you could undo the nut, and then this socket would be, if you like, remain internally when the front's pulled away towards you. But as you can see, it's actually got a flange here, and it's the nut for that is on the inside. And of course the depth of the test set here front means you can't get any pliers on the back or spanners or whatever. So yeah, it is a bit strange, but as you can see on the front as well, the variable control, there's no actual screws on the front of here that fasten this to the front panel. It's done from the other side, so we have to undo this collar here for the volume and the contrast control, because that's on the same PCB. So once we withdraw the front from the unit and turn it up, then we'll be able to access all the screws that fasten the variable control. I thought that the diagonal screws that I pointed out earlier on that PCB held that control board to the front of this test set, and it doesn't. It's just the body, the plastic bodywork on the Hall effect sensors for the spinner, the variable control, is quite large, and it was actually screws that held that together rather than fasten the screws, the circuit board to the front of a test set. So you have to remove the front and drop it down in order to then access the main screws that hold the PCB in, that covers all this area all the way around, in order to get at it. So it's a bit of a stripped down job, but you know, we're nearly there now, we're not far off, and it may be possible. I'm going to read the manual a bit further to see if there's any additional screws that I can remove on the front here, but I don't think so, to be honest with you. There is one screw there, but and another screw here, but again, all these sockets have to come off this panel in order for that aluminium panel to come off the front anyway. So we're going to have to, no matter what, disconnect that coaxial cable there, the SMA, and bend the cable down so that the front of the unit can be withdrawn. Bit of a pain, but I suppose that's the only way to do it. I don't like bending things, you see, if I don't have to, but it does say in the manual to bend the cable out of the way as well, but it just seems a bit brutal. But anyway, we'll see what we can get done. Right, well, we bent this coaxial cable out of the way now, and we're making some progress. So we got that out of the way, we bent it out of the way, and we're making some headway. The plastic thing here, this gets in the way of that stud proud rivet thing down there, so but it's coming apart. I've just got to try and coax it. So I've got to bend this plastic thing down that holds that tray there, and then out it comes. There we go. So now we've got the front detached. Just unplug this connector here, and that way then it can truly fold away. So now we can get to things which otherwise I wouldn't have been able to. So I can obviously get to the just lay it down on the bench, so I can get to things that I wouldn't have otherwise been able to now on this test set front. So I can get to the module for the inverter. All the screws and everything are accessible now with the look of it for the PCB that deals with the variable control. So yeah, so we're nearly there now. Right, now we can access these screws that are diagonally, which I believe hold it in, this PCB. So we'll remove that one, and looks like that's the case. And then the other one, which is down there, looks like it, and that should allow us to remove this board then, with the knob on it, all being well. Hopefully it don't get trapped and 1,000 other things to take apart. I can see the magnet disc. Is it going to come out, or is it fastened somewhere else? It's fastened to other things. Interesting. I'll look at that in a bit more detail, I think. But I can see the magnet there, and these are the, look like the Hall effect in these enclosures at the ends here. So we'll need to have a look at that in more detail, I think. But it appears to be attached to some wiring which goes off to this thing there. So I think I'm going to have to either unsolder those wires or remove this potentiometer so that that comes with it, and then the whole loom comes with it. But yeah, interesting. Right, let's see what we can do. Okay, so just looking at this board here, we zoom right in. The Hall effect devices are just here, B1 and B2, these two. But I have noticed, looks like these two, that one and this down here, they're magnets that repel the indents on this disc, because obviously this disc has got north south poles all the way around it, so that there's two permanent magnets with field poles that are very, very sharp, as you can see just there, those little metal things, and two there that effectively give it its indentation. You see, it's going round, it's repelling it. And then we've got the two Hall effect devices that are pushed up against the magnet. Now you might be able to see there's iron filings stuck to this. There's one there, look, you can just see it there. That's an iron filing, and you know, you can just move it about. Another one there, which is just coming into picture there, that's an iron filing as well, which you can move about. And there's quite a lot when you look down the longitudinal area here. You can see there's like lots of like hairs, iron filings stuck up. So I'm wondering if it's contaminating these Hall effect devices, and we're getting some contamination on them, maybe. Possible, may not be. So might be worth a look at that. And it could also be that those Hall effect transistors, sensors, need to be pushed up against the magnet a bit more, or perhaps even brought out, because one of them looks like it's pushed up against the magnet more than the other one is. So may need some adjustments there, cleaning up and adjustments. Looks like undoing this screw and this screw allow the whole plastic assembly that carries the spin wheel and the magnet assembly to come out, leaving these two exposed on the PCB. So I might do that and take a look. It'd be nice to be able to power it if I get the right pins on here on the service manual with 5 volts and then 2 pull-up resistors as described. Turn this and see what the pulse train's like coming out before we do anything. So that's an option. Might need further analysis that way. But we've got a voltage regulator, an LM series voltage regulator, then a diode and a high precision resistor, transistor here as well for controlling other aspects of the brightness and contrast control, I think. So it'll just be a case of finding the right pins on this connector and then doing some tests, I think, with the oscilloscope before we go any further. But there's definitely contamination on that wheel with the iron filings that are appearing left, right and centre on it, so it'll need to be cleaned, because there's quite a bit there. There's another one, look there, that's just coming into view, and yeah, there's quite a bit of contamination on that magnet. There's some contamination on there that the video camera's not picking up very well, but I can see it with the naked eye under a microscope. So yeah, it's quite heavily contaminated, is that. Right, let's have a look at the next bit. Okay, so to show you what I mean exactly, greater detail, if you have a look here, you might be able to see, if I zoom in, all these iron filings. You can see them there, all those little black dots. They're all filings. Big piece of metal there, stuck to it. Loads of filings on it. And obviously, if you look at in between there, potentially, see if we can get a bit more light on it. Might be that looks to be some contamination already. From what I can see down there, I can see something stuck to what appears to be stuck to the front of those Hall effect devices. But not good. So that's definitely going to upset those all effect devices out, I would have thought, having all these filings and things, as you can see there. So yeah, interesting. Very bizarre. Very good. Okay, we set up an experiment now where we're going to power this board to do some tests and measurements, and we've, as per the recommendation in the service manual, we've applied 4.7k resistors between the 5 volt supply rail and the sensor, the Hall effect sensor outputs for both pin 3 and pin 4 on the socket. So I've soldered 2 resistors in there to pull up the lines. So we've set the power supply to 5 volts DC at 100 milliamps maximum current in case any shorts, any smoke. And then on the Rigol scope, I've set that up so that it's DC coupled at 5 volts per division, and on both channels 1 and 2. Obviously channel 1 goes to one Hall effect sensor, channel 2 goes to the other. So we'll be able to look at the waveforms on there. I slowed the time base right down so that what I'll do is I'll turn this control and I'll count out 1, 2, 3, 4, 5, 6, and each time I call out a number I'll do an indent within the control, so it's a couple of hertz in frequency. So because I've slowed the time base down, we're able to see the signature of both sensors at the same time and compare them. They'll be displayed out of phase, or should be, but essentially the pulse train should be identical in amplitude and frequency, but out of phase on either the amber trace or the blue trace. So anyway, we'll see what happens. So if I do zoom in now on the display on the oscilloscope, and we can have a more detailed look at that there. Right, so if I count out as I'm going, so each indent will be as per each number I count out. So that's 1, 2, 3, 4, 5, 6, 7. I can already see a problem there, look. At the top, the amber trace in comparison to the bottom, it's all going erratic. It's not keeping in synchronous with the bottom. It doesn't help when the screensaver comes on, does it? So, right, keep turning. 1, 2, 3, 4, 5, 6, 7. So you can see the frequency of the bottom waveform is more or less identical and uniform in mark space ratios. I'm turning the control and it's basically noise free, whereas the top trace is one of the Hall effect sensors, and at times it does read correct like there, more or less, but then all of a sudden it just starts giving out false pulses like you can see now. And of course there's quite a few false pulses there, considering it should more or less be out of phase with what's displayed below. So you can quite clearly see how it will confuse the microcontroller in the test set and start to think that it's going one way or the other. Right, I'm turning the control counterclockwise at the moment, and as you can quite clearly see there are various pulses in the top trace which are showing up pretty bad. So I'll now turn it clockwise. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you can see it's really bad, isn't it? The top trace. It keeps it sometimes, and then other times it's just not keeping up with it, is it? So I don't know whether it's iron filings that's contaminating the sensor, or whether it's a faulty Hall effect sensor. And we've got two pulses very close together there with considerable mark space in comparison to the bottom trace. So we can see it's going all Pete Tong, is that? It's definitely not having the best of days when you look at the top versus the bottom. So yeah, I'll just have a look at that in more detail actually, but let's just zoom in on that, I think. You can clearly see serious problem there with that Hall effect sensor. The pulse train's way out of kilter on the top, on the amber trace. Sometimes it's more or less right. Oh dear. Yeah, and even without turning it as well, if I just press on the plastic wheel itself, push down on it without actually turning the wheel, then already we can see the top trace is starting to show some erraticness there, whereas the bottom one isn't moving. So if I zoom out so you can sort of see that more clearly, and if I just press down on that, physically press down on it, you can see just tapping it even causes it to do weird things. So this goes back to original fault symptom, where if you grabbed hold of the spindle, the knob, and pulled on it or pushed on it while turning, it seemed to make the fault go away and come back, and you could adjust how accurate it was, or at least try and get it to work. So you can see there, just by pressing on the magnetic wheel, that it's already causing instability in the sensor. So yeah, very strange. But as you can see there, if I just do one little increment at a time, you can clearly see in periods it will start, yeah, as you can see there on the top trace, in comparison to the bottom, it's just not keeping with it. You get these erratic pulses. Sometimes you get a whole chain of them all occurring at once, like you can see there, and then other times it's fairly straightforward. It works for a little while. So, and I think it's as those filings are going round on the wheel, or it could be the proximity as well of the Hall effect sensor. But I think first thing to do is remove the magnetic wheel from the PCB, clean the magnetic wheel up, get those iron filings off it and contamination, clean up the Hall effect devices using isopropyl alcohol, and then reassemble everything, and let's try it again, see whether that sorts it out. If not, then it'll be looking at getting some new Hall effect devices to replace them with. And I think there are 3 types of Hall effects, if I remember rightly from my school days. There's unipolar, bipolar and linear. So yeah, I think this type is a bipolar device, so we'll look at the part numbers on them and see whether we can pick them up. But as you can clearly see there, as I'm just incrementing that disc, as it's just going round and trying to keep the same frequency as well as I'm notching each indent, you can clearly see that there's some major problems with that pulse train on the top there. So yeah, definitely a strange one is this. Also, we'll check for dry joints as well, and soldering on the devices. There's a couple of through holes as well, I've noticed, on the PCB in places, which has connected the signal in wires to the actual pins on the socket down there. So it could be some through hole as well that might need soldering, but just disturbing the board, just touching the wheel without turning the wheel, causes a pulse train to develop, as you can see there. So very strange, very strange. Right, let's strip it down now and try and clean it up. Okay, so we've removed the magnetic wheel. It was filthy, this, absolutely filthy. The wheel itself was absolutely hacky. It's filthied the rag that I used to get all the iron filings off and everything. Just a bit of foam cleaner and just wiped it, you know, so the iron filings stick to the disc. But it's nice and clean now, and I've checked it under the microscope and turned it, and it's very nice. Nice action on it. You've got your two horseshoe magnets in there, permanent magnets that repel the magnet north and south poles on this, because obviously if you look through the top you can see the magnets that are arranged inside the wheel individually. So this ferrite on the outside, or this magnetic material, conducts those poles to the outer, and that's how you get that indent sort of thing. So that's nice and clean now, and free of contamination, so that's pretty good. And you've got to be careful with it. I just dropped it there by accident, but you can break that thing very easily, this outer collar. So you've got to be really careful because that material's so delicate, so just be careful when you're handling it. And as for this, we've got the nice little effects there, the Hall effects transistor, all effect devices, but there's a couple little through holes as well on this PCB, so there's a couple of little through holes. Not sure if you can see those, if they'll focus or not. Well, it might do. Might focus on that. Maybe if I put my hand at the back, it might get them in, maybe. But yeah, there's a couple of little through holes as well on this PCB, various places, particularly down this area at the bottom. So resolder those as well, but I'll just reassemble it as it is. I can always manipulate these closer to the magnetic disc if I need to, and just check those. But we'll reassemble it and just have another little test and see what it does. Okay, put it all back together, but it's still the same. So what I've done, I've bent the Hall effect, one of the Hall effect transistors away, Hall effect sensors away from the wheel, which is this one here, and just to isolate which one it is out the two. So when I turn the wheel on this, because we're still looking at both channels, you can clearly see in a moment the bottom trace is more or less uniform, so that's good. But the top trace isn't measuring anything at the moment, because obviously the Hall effect sensor has been pulled away from the magnet. Now if I push the Hall effect transistor sensor back up to the disc, when again you can start to see in a moment when it sorts itself out with the pulse train at the bottom compared to the top. The top's gone erratic completely. It doesn't matter what you do with that Hall effect sensor, whether you push it closer or pull it away, that pulse train never gets any better. As a matter of fact, I'm just going to try and edge it out just a little bit away from the disc, a couple of millimeters, which I've just done there, and we'll just try again and see whether that improves things. But I can see already it's gone highly erratic as the top pulse is there. So one of the Hall effect sensors isn't working properly, and the other is, which is signified on the bottom of the trace there, so in the different colour. So yeah, it looks to me like as if we've got a problem with this bottom Hall effect device there. So if we look at that more carefully, and it's this one there at the bottom, that one out the two. So I think we'll have to order some new ones. I may as well replace both of them rather than just one on its own. It's hardly worth just replacing one only to find the other one fail shortly afterwards. But yes, very strange. I'll see what the part number is now, and hopefully, fingers crossed, we can get some ordered. Back soon. Okay, so as far as this PCB is concerned, there's a couple of other functions that are dealt with on this board, which if we look at the diagram, we've got the contrast control, which is the variable control on the front of the instrument, and as well as that we've got a temperature dependent resistor, and then we've also got a voltage reference as well with the Zener diode, and this controls the minus supply to the LCD display to set the contrast levels. So insofar as the temperature dependent resistor is concerned, that's this device there, and obviously we've got the Zener next to it, so temperature dependent resistor, Zener diode. We've got a couple other devices. This LM regulator here is basically what's referenced there on the diagram for the contrast, which is obviously the LM337T at the top. So that's what that does. Hence the reason why in the front panel there was those two wires which solder onto these terminals on the rear. There's two terminals there, that one and that one, and there for the variable control on the front of the instrument. Okay, so we've taken the inverter module out of the test set, and as thought, it's potted, so you can't actually get to any components in it and repair that module if it's failed. And it looks like it's well and truly potted as well. It's not just like a coating on this end and then you can peel that off to get into it. It's full of it, so there's no way that module's repairable, I'm afraid, and it sits there for the backlight assembly for the display. So I've just backed this pin out the socket, and which this connector mates with. Notice this little bit of metal here was bent out of position, so I just bent it back because the pin of this actually goes into it sort of at that angle, goes in like that. There's a tiny little hole in the top there that it goes through, and it pinces it. So just squeezed it together a bit, and then what we'll do, we'll reattach that back into the socket and see what happens. Okay, so we've replaced the Hall effect devices now. I'm just going to turn the wheel just one click at a time, roughly one every second, or one indent. And as we can see there, the waveform's a lot better than it was. It's identical with the bottom, more or less, so that's good. So we'll just turn the... So I'm quite happy with that. I've replaced both Hall effect devices. I'm just continuing to turn it, and as you can see, we've got more or less a uniform pulse train top and bottom. So if I try and turn it quicker, just alter the time base on the thing, just so we can see it more in real time rather than in slowed down time. Okay, so if I just increase that somewhat, and then we just want to zoom in if I can, give it a spin. Now if I slow that right down, yeah, we're seeing a nice signal there, which is what we want. That's okay. Yeah, a lot better. Is that a lot better? So I'm happy with that. I'm very happy with that indeed. I'm very happy with that. See if I can get the time base to widen. Okay. Right. Yeah, so that's, I like that. I like that. I like that very much. Nice uniformity there between both sensors, so I'm quite happy with that. So I think that's been quite successful, considering. So anyway, we've put the two new ones on, and I think it's time to reassemble it now, and fingers crossed it'll work when it's all put back together. So I'll join you again when we've reassembled the test set and we're ready to do some tests. Okay, wonderful stuff. We've finally got it back together, more or less. We've only got the covers and feet to put back on, but I just wanted to double check everything was working. And if I just switch this off a second, just so we can demonstrate it a bit better. We've got here the RF level or frequency we can set, so I can spin the control and obviously increase the frequency without a problem. Likewise, I can decrease it as well, not an issue. If I go to RF gen level, and then we can again increase the level, and as you can see, it's very rapid, very quick, whereas before it was always dragging its backside and missing the beat. So this is straight down. We've now got the 0.1 dB resolution that we didn't have before, because if you remember, it was skipping a lot, going in big chunks even when it was more or less working. Before then the other fault developed, which is where it just started going down to the minimum level, which is about neg 131, neg 134 dBm there, and then likewise it would carry on going up the scale to the maximum RF level that it could put out, and thus obviously say the same thing, you know, to higher level. But as you can see there, quite nice control of the output level without any issues up or down. So I believe that's repaired it. I've had the test set on for a good couple of hours, been playing with it just to make sure that, you know, fingers crossed, as we've had in other repair videos. Sometimes things can be, you know, still be faulty when you think you've fixed it, especially with faults that are intermittent in nature or that come with temperature changes. But I'm fairly confident that we've repaired this, because it would have gone faulty before now. Because in previous tests we did, you'd only have to have the instrument on about 30 seconds to a minute before it started playing up, and this has been on now for quite some time. And just to note on this as well, this CMS33 radio test set, one of the early models, had the UGN 3020 Hall effect switches sensors in them. But I have noticed, looking at the CMS 52, 54, CMS 57 I think it is, service manuals, all those instruments that came after this, newer ones, had the UGN 3120 devices in them instead of the 3020s. Now that's interesting, because the ones that I've got here from these are old stock RS components one. They come with a little bar magnet as well inside, which you can see. I've saved the old device there, one of them, because that was working, but the other device I've labelled up as defective and put in this bag, which is a one that was playing up, giving the erratic signals. But yeah, this device is actually UGN 3120. That's what's written on it when we installed it into the instrument. Now my thought is perhaps there's been a product change due to reliability issues, or perhaps a manufacturer of the All Effect switch superseded the UGN 3020s with 3120 because of the issues perhaps they were having with them. It could be a common failure, or it may just be that the 3120 naturally superseded the 3020s for whatever reason that may be. Perhaps they have better specification as well. But it's quite interesting that, because the CMS33 service manual makes reference to the 3020, but all the newer models that came after this all employed the UGN 3120 device, which is what we fitted today. And it's certainly made a difference. I can say that it's very refined, is that control now in comparison to what it was before, and it's straight there. So I wouldn't be surprised if Rohde Schwarz cottoned on to that perhaps and changed the design a little bit and employed, as I say, the UGN 3120 in place of the 3020. That could be what they've done, or it could just be the manufacturer said, well, the 3020 is no longer available, we now make the 3120. There are actually 4 devices in the range, which is a 3113, a 3120, a 3130 and a 3140, and they're all Hall effect switches, high temperature stable and stress resistant sensors. It says best utilised in applications that provide step magnetic slopes and low residual levels of magnetic flux density. So yeah, and it says as well on the specification sheet I'm just looking at now, it says each device includes a voltage regulator, a quadratic Hall effect generator, temperature stability circuit, signal amplifier, Schmitt trigger and open collector output on a single silicon chip. And the onboard regulator permits operation with supply voltages of 4.5 to 24 volts DC. The switch output can sync up to 20 milliamps. With suitable output pull-up, they can be used directly with bipolar or MOS logic circuits. It says the 4 package styles available provide a magnetically optimized package for most applications. So suffix LT is a surface mount SOT89 or TO234A. Package suffixes LLU and UA feature wire leads for through-hole mounting, which is what this is here. So yeah, quite interesting. I've been very pleased that it is working, so much so now that I feel confident to put the lids back on. I think I've also learned a little bit myself today with taking the instrument apart, because I haven't done a full strip down on one of these for quite some time, and the process was fairly straightforward. The manuals for them are very well written, even though the manual I have is half German, half English. You have chapters written in German and then chapters written in English, so it takes a little bit longer to find things, but when you do find them, it's very well written. And the manual was quite helpful with the technical information, as we saw earlier in the video. I did end up, though, chopping the plug off and the socket for that inverter, you know, for the display, because the display was flickering and it was terrible. And it was this this socket here, this awful socket and plug, and even though I had the pins out of this socket, and I sort of crushed them, the little receptacles, squashed them in again, and it never really gave a satisfactory connection. It plugs together, don't get me wrong, but it doesn't plug together in my mind properly. It's very loosey goosey, and it doesn't want to. It pushes in very loosely. I mean, you can see there. It's just, you know, it'll just drop to bits. And I couldn't. I managed to do it so that when the socket and plug went together initially, it was tight, but once you just gave it a little jiggle, it loosened again and it just came out. So it's as if the metal in the receptacles in the socket had lost their memory. You know, metal with memory, where it's like a spring metal and it'll spring back to where it used to be. Well, this has lost that sort of ability. Again, don't know what's happened there. And this socket, when you look at the profile, it is different in the profile to what the plug is. The plug is narrower and it's very loose, as you can see there, you know, and it's obviously dropped off now, but it's a different profile, if you like, to the socket. It just seems such a bodge job, does that. But anyway, what I've done, I basically took the wires and I spliced each wire, then twisted the stranded wires around each other, soldered them, and I have this which I found in my little box of tricks. I had a bag of, and I don't know what I've done with them. I've just put them down somewhere as usual, and I can't find them, but I've got a bag. Oh, hang on, I think I might have them over here somewhere. No, but anyway, I have a bag of sleeves that go over the wires to protect them, that just push on, and they're made of rubber, and they just, you know, cover the wires, so you've got this nice sleeve over the wires to protect them from having any issues. So that's what I did there, because I didn't trust that plug, and these test sets do suffer with that issue with that socket. Now, just a bit odd, you know, but yeah, very odd, very odd. So these are things are sent to try us. Oh, there we are, look, that's where they are, they're hiding there, look. So these are them again, something else from RS Components, but these little sleeves are really good for sorting issues out on them, you know, on these test sets. So yeah, very pleased, managed to get the thing going, and I think all it remains to do now is with the just final fastening up of the unit, and that should do it, I think. So yeah, quite an interesting little instrument. Obviously tricky to repair, like they all are. Quite a challenge to strip down and know how to take the instrument apart, but I think this instructional part of the video that you've followed here will give some instruction on how to do that. So yeah, I think it's been quite an interesting journey. Thank you very much for watching. I think we've reached the end now, and if you like the video, please subscribe to the channel. There'll be more repair videos, and keep your eyes out for even more test gear repairs. And with that, thank you very much and goodbye. See you in the next one. Bye for now.